G'day everybody, where's Wally here? Well, I think I've given Antonio enough rope to hang himself, so let's go and have a look at just what he's been doing with the ISS and Red and Astronomy Live's triangles. Let's just go and have a look.
And they're angling, by the way, a lot. Come and debate here, come and debate. Like, no, I've been on that. I've done the rounds doing that. I know what you guys do. You pull it immediately. So no, not interested. Sorry. You have to deal with the consequences of your actions. Responsibility.
Wow, so much self-delusion, Antonio. You know, you could get this debate back happening again if only you would apologise to Simon Dan.
Okay, now we're going to look at how, from this, which is their supposed observation, you can you'll be justified in assuming that these were two individual observations, not a joint effort. They're not the same distance away from the center line. They're not at right angles to the center line. In fact, it could be two separate observations on two separate days.
Two separate observations? Really? It is not possible that the ISS will be over the same path at all. Have you even looked at the path, the tracks that the ISS takes on consecutive days?
I don't know.
It's not even the same.
I don't know.
And the moon's lunation will be different. Someone observant like Antonio Superrats would notice that.
I don't know.
And it's going to be 13 degrees away from where it was the night before, so Antonio Superrats would notice that.
I don't know.
And the weather could be quite different. There's just really no way that you could make two separate observations on two separate days. But I tell you what, the one thing that does make sense is two different observations at the same time on the same day for the same pass of the ISS. That is just simply the easiest way to do it.
I don't know. This is mooncalc. This is Red's location. This is the center line where the ISS transited, where you'd have the ISS, you're seeing it going directly over your head.
No, Antonio, you're wrong again. It's not directly overhead, but the ISS is seen passing directly between you and the center of the moon. So the center of the moon, the ISS and your eye are all in alignment, not necessarily overhead.
I don't know. And this is Astronomy Live's location. Exact. Now we're going to compare Astronomy Live to the center line and the center line to Red. Pay attention to the moon azimuth. It's over on your left. That's what we're looking for. Astronomy Live's moon azimuth is at 234.35. The center line is 0.34 and Red's is 0.33. That leaves 0.02 for their triangle to the center of the moon. That's right, it's as simple as that. Their triangle to the center of the moon has a 0.02 convergence point at the point where their lines of sight meet at the moon. That's the shape of their triangle. Whatever observations take place, they take place within that first.
No, actually that triangle is the green line. They are outside of that. So all you can factually say is that their triangle must be larger than 0.02 degrees, and 0.1212 is. So we're all good.
Huh, it's interesting. You could have just parked on this road, walked down and set up there. But no, don't need to. Especially if you're not going to actually take angles into account. So you see here, this is where Astronomy Live was. It could have been over here. Huh. Good Lord. Globlings lying and distorting. Oh, would have thought of that.
You do realise, Dim Dim, that the small misalignment doesn't change the answer at all. The effect of that misalignment is that the transits are a few fractions of a second further apart. It's a discrepancy in time, but not in space. They accounted for any slight potential discrepancy by measuring the distance to the centre line at right angles. So, the rest of Antonio's reasoning from this point is all based on one claim, which is wrong, and therefore there's no point in me debunking any of it any further. It's the wrong triangle, mate. Again, you've got it wrong. Can you see?
I don't know.
Can you see the solid green moon calc azimuth is not the same as red and astronomy lies parallax triangle? Can you see that?
I don't know.
And while we're at it, it was a very smart move of you to get the debate cancelled, Antonio, because if this is the only evidence you had, you would have been kicked out in the first 10 seconds.
I know.
Yeah, I just cannot believe that Antonio would do this so stupidly. It's either stupid or on purpose. I mean, who would ever think that looking at a triangle to the centre line of the moon is anything like looking at a triangle to the parallax of the ISS? Remember, the moon is now, what, 750, 740 times further away than the ISS? And of course, no one's ever actually seen Antonio do any maths on screen, apart from multiplying one number by another number. And even then he used the calculator, but I haven't seen him actually do any trig. And thanks very much whoever gave Antonio the link to the triangle calculator. That has really made him a lot more fun to be around of late. And you really should learn to check things before you make an embarrassing video about them. And if you have any complaints about this comment, please send them to me at my address.
Parallax, you say? May not think so. In fact, I was going to work on this. I was going to explain this. What Red and his pal have actually shown is that the moon is not at the same place in the sky for the two observers. That's right, it mimics parallax, but when you bring the supposed distance into it, it's like, good gosh. And I meant to show this. In fact, I discussed this with a pondling friend of mine, and we're going to do it one day. I have a P1000 and a pretty powerful laser. We're going to point the laser at the moon, and I'm going to move away 1 kilometer and film the moon. We'll film first from the laser, and then I'll go 1 kilometer away and I'll film the moon. When I'm filming from the laser will be pointed at the center of the moon. When I'm filming from 1 kilometer away, it will have taken me only a few minutes to get there. The moon will not have moved so much, but in any case, I will have asked him to track the moon, placing the laser in the center of the moon. For when I'm filming it from 1 kilometer away, what will we find? That it's not pointing at the center of the moon any longer. Oh no! Is the moon holoprismatic like the sun? Yes, but you don't have to believe me, of course.
Holy holoprismatic projection, what exactly is that? Okay, Antonio, let's just see how fast the moon moves. And I'll see if I can point my laser at it. So Antonio thinks that the moon won't move far in 2 minutes. Well, just check this out. I've pointed the P900 at the moon. Let's just see what happens for the next couple of minutes. And the moon is moving at about 14.5 degrees an hour, which at a goodly high zoom will move out of frame in about a minute or so. So I doubt that Antonio will be able to get from one location to the next 1 kilometer away and then set up his camera and take another shot. The moon will have moved. And I seriously doubt that you're going to be able to see the laser from 1 kilometer away, as I'm even struggling with my super burning blue laser, getting it to be seen almost a meter away. So I'm not sure how you're going to go there. Anyway, Antonio, I was thinking you really need to have a go at the red tube experiment. It was one that Critical Think came up with, I believe. And it's a very clever, super simple idea. It's very well designed and it will prove globe or flat. You really should give it a go. And when it comes to seeing lasers at distance, I thought I'd ask an expert, bring in the expert witness, and I wonder, can you see a laser that's not pointed straight at you? Well, there's this pilot guy I know who used to fly a helicopter, and he's had lasers pointed at him from the ground at night. And yes, you can see them well and truly when they're pointed straight at you, but they don't need to be too far off of you, and you can't really see them that easy. Anyway, they went and landed the helicopter, and they arrested the guy. Poor fella. Who would like to have Wolfie knocking on your door at 3 AM in the morning and saying, hey, get out here with that laser? Not me. Well, when I spoke to Wolfie about the possibility of doing a laser pointing to the moon from 1 kilometer away, when he stopped laughing, we thought that it just really wasn't possible. I think his exact words were, please encourage Antonio to try it because I would love to hear his excuse when it doesn't work. Something like that. And one final thing I wanted to mention for all those avid ISS watchers, in the southern hemisphere from about the 14th to the 19th, all nighttime passes will be visible passes. And that's because the orbit, the inclination of the orbit of the ISS is going to line up with the terminator for a few days, and because it's almost the solstice, the ISS doesn't go into shade at all, so it's having a 24-hour sun type event, which is really, really cool. So in the southern hemisphere, from about the 14th to the 19th, all nighttime passes will be full visible passes. There'll be no diving into the Earth's shadow halfway across the sky for a week. This would be really cool. Anyway, that's enough of Antonio trying to make things not work out. He's really doing a terrible job at it. But we can all see that he's got some really incredible motivated reasoning. Antonio just so much wants this not to be true that he'll go to any stretch to do it. Well, of course, Antonio has been in full damage control, obsessing about right-angled triangles and isosceles triangles. Well, what I did do that Antonio didn't do is to see, does it actually make any difference? Well, the answer is no, it doesn't actually make any noticeable difference. So what I did was the calculations both ways. I got a right-angled triangle on red side, which is the same as a right-angled triangle on astronomy live side, and then I did an isosceles triangle. And guess what? The difference is less than 1 kilometre. Indeed, it's only a few metres difference, so it really doesn't matter at all. And then I went and had a good long hard look at what Scott Manley did, and he used a slightly different method. And of course, anyone who knows some trig would realise, he realised that it's a long skinny triangle. And when you've got a long skinny triangle, to get the distance of it, you just divide the baseline by the angle in radians. And guess what? It gave us the same result too, so there we go again. Anyway, this is enough dim for one day. Let's go and re-watch our favourite space nerd Scott Manley do the same ISS height calculations using 2 cameras and the sun this time. At the end, he actually comes up with the speed of the ISS as well, because he's a little bit more clever at maths than you are, Antonio. I know a lot of us have already seen it, but I really want Antonio to see it. And if he doesn't look at it soon, I'm going to have to do something even more drastic.
Hello, it's Scott Manley here. Now, in last week's video about the SpaceX launch and Fleet Week, I mentioned one other thing that I took a picture of. The International Space Station, travelling between me and the sun and giving me a good look at the structure, showing the solar panels. Of course, if I slow things down and stabilise it, you can get a much better view of this. No, it's not a TIE fighter. That thing is the size of a football field, and I don't believe there are TIE fighters that large in the Star Wars universe yet. Anyway, I was of course able to do this because of a website called Transit Finder, which allowed me to predict the transits and get a camera in the correct location. I actually had pointed out that if you stood in the right place, say the top of the Salesforce Tower, you would have been able to see the Blue Angels, the International Space Station, and a rocket launch all within a few hours of each other. So that was a pretty awesome day. But I wasn't content merely to look at this, I actually wanted to do a bit of science. So I got my daughter Sky to stand in a slightly different location with a video camera and capture the pass. And there it is there. You might have barely seen it because this video camera is a pretty cheap old camera. Optically, it only has a factor of 10 zoom. Digitally, it gets a little bit more. But that's just enough to see the shadow and show where it is. Now it spends less than a second in front of the sun, essentially travelling in a straight line. And because the locations are about 1 kilometre apart, it passes over a different part of the sun as viewed from each location. To make it more obvious, I put a line through the shadows and then aligned the 2 passes so that they appear to move in the same direction. And then, yeah, once you do this, it becomes very obvious that one is slightly to the left side and one is slightly on the right side. So now the question is, how big are these differences? So I'm measuring this in solar diameters because that's a reference point. So one's 0.44, the other is 0.63, measured from the left side of the sun. That means the difference is 0.19 solar diameters. Now the diameter of the sun changes by a small amount, but it's roughly 32 arc minutes. If I was doing this really accurately, I'd obviously measure the exact size of the sun, and then I'd make sure that the cameras were calibrated to use the same, so that we're returning the same edge. But look, I'm just going to use this, and it gets me a parallax of about 6.1 arc minute. That's about 1/10 of 1 degree. Now, to get the distance to the space station, I need to know how far the base stations were apart. So I go look at the map and find out where I was and where Sky was. Sky was standing up there in those trees because it was very windy. And I had moved about 1 kilometre away, standing down close to the water, hoping that the water would actually calm the amount of heat haze that I was getting from the land to try and get more resolution. But yeah, measuring it in Google Earth came up about 1,080 metres. But that isn't the actual baseline, because what I'm doing is measuring the angle difference between two different tracks. And the tracks are going in a specific direction, and if I happen to have my two base stations sitting along that track, then I would have no separation. So what you actually have to do is measure the distance perpendicular to this, at right angles to the track. So this is the track that I got from the prediction site. So I've overlaid that on the map and yeah, measured the angle. It's about 79.5 degrees difference, which actually means the difference is very, very small. It was pretty close to being perpendicular. I could have skipped this step entirely if I'd just been lazy. So now what we have is a really simple triangle. We have a baseline of 1,058 meters and we have a very, very tiny angle at the other side of 0.102 degrees. And given that this is a very thin triangle, all you do is you divide the baseline by the angle, but you have to convert the angle into radians, and you get 596 kilometers. Now that's pretty cool that I could actually see the solar panels on the space station from almost 600 kilometers away. But what I really wanted to figure out is, what is the altitude of the space station? So when I saw it, the sun was 43.1 degrees above the horizon, so I have another triangle situation here. All you do is you multiply 596 by the sine of 43.1 degrees and you get 407 kilometers. And I'm, again, quite chuffed at how close that is to the real thing. If you Google it right now, I think it'll come out as about 408 kilometers. I would have loved to actually check the exact altitude on this date, but that website doesn't appear to be working for me right now, so I'm just going to have to presume that it's pretty close to this number. The other thing I can calculate is the speed of the space station. Now, it's coming towards us, we know the distance, we know the angle above the horizon, and we can figure out the time that it took to cross the sun. I count 28 frames. My camera is running at around 30 frames per second, so that's about 0.93 seconds. And because it passes slightly off the centre, we figure out that it covers 96.8% of the solar diameter. And if we take the diameter of 0.533 degrees that we used for the sun, and you multiply that out, we get an angular velocity of 0.00965 radians per second, which at that distance corresponds to 5.75 kilometers per second. Now that is probably pretty low in your imagination, and the reason for this is the spacecraft is not moving exactly perpendicular to our viewpoint. It's actually moving across the surface of the Earth. So if we take our 43-degree elevation and assume that is the angle it is moving relative to our viewpoint, then we should divide the 575 by the sine of 43.1, and you get 8.4 kilometers per second, which is actually now too high. But part of this is because the Earth is curved and the spacecraft, the ISS, is coming up over the horizon. So instead, we can convert it to this three-triangle where we know the distance to the ISS, we know the radius of the Earth, and we know this interior angle. So you can convert all this using the cosine rule and figure out that the ISS's altitude is 421 kilometers. That's a bit too high still. And but the angle of the motion relative to the observer is about 46.77 degrees, which gives us a more reasonable speed of 7.9 kilometers per second. And I was all ready to say that was mathematical errors until in the shower a few minutes ago I realised I'd forgotten to account for the sun direction, which is 20 degrees offset from the motion, so there's an extra 20-degree angle there I didn't incorporate, and when you add that in, you get a velocity of 7.4 kilometers per second, which is pretty darn close, especially when you consider that you should also subtract out the rotation of the Earth. I think this is getting pretty close to the real thing. Now this isn't the only way to measure the altitude to the space station, but honestly it was an excuse to take these kind of pictures, which is always pretty sweet. If you want, you can also just simultaneously have two cameras snap the same picture. That requires time synchronization. If you can just record tracks across a starlit sky, again that requires a little bit of math to make sure you get it all figured out. I like this version because it makes sure everybody is pointing at the same space at the same time, and therefore the amount of corrections you might need to do are minimized. So yeah, there you go. With some photography, bit of geometry and math, you can show that the space station is indeed about 400 kilometers above the surface of the Earth. I'm Scott Manley. Fly safe.